In this video, we're going to look at how Newton's second law of motion and some principles of vector calculus can help us show the principle of conservation of energy. So, how does all that translate into vector calculus? Well, Newton's second law of motion says that force equals mass times acceleration, which means that if a particle is moving along a path x of t, then the force at that point on the path is going to equal the mass of the particle times the second derivative of that path function. So that's our force equals mass times acceleration. Now we need to introduce another term. Let's suppose that F is a conservative vector field. That is a fancy way of saying that F is the gradient of some other scalar valued function v. Specifically, for reasons that, kind of matter, we're actually going to say that f is going to be the negative gradient of a scalar function v, and we call that the potential function. Part of the reason we have that negative sign is because if we look at the flow lines of f, and we plug those into v, then if you follow the flow lines, you're going to go to lower and lower values of the potential function. So, in other words, if you compose the potential function with those flow lines, you're going to get a decreasing function. And that's actually the result of one of the homework problems in the text. So, we have f is the gradient or the negative gradient of some potential function v, and we want to show this idea of conservation of energy. In this case, what that means is that 1/2 m times the speed plus the potential function is constant. How does this translate to what you might expect? Well, this is saying that 1/2 times mass times the speed squared is going to be what we call kinetic energy. And plugging in x of t to the potential function is going to be potential energy. And we want to show that basically the kinetic energy plus the potential energy gives us a constant function. The best way to do that is to show that the derivative of this sum is 0. How are we going to do that? Well, first of all, whenever I see a norm, especially a norm squared, I am just incredibly tempted to turn that into a dot product. So I'm going to rewrite this as 1/2 m times, oh, no norm sign. I want to write this as a dot product. We'll have x prime of t dotted with x prime of t plus v of x of t. Now I have a couple terms. In this first one, I'm going to use the dot product formula for taking derivatives. This 1/2 m is just a constant. I'm going to have 1/2 m times, well, we'll have the derivative of the first, that's going to be acceleration, times original of the second, dotted with the original of the second, plus original of the first, dotted with the derivative of the second. And we're going to be adding we'll take the derivative of this as well. I can go ahead and get rid of that 1/2, or don't know actually why I had that in, that's why I had that in parentheses. Ooh. Okay, so that's our first term. And then for our second term, we're going to have some chain rule going on. So this is going to be the gradient of v by the chain rule kind of written for vectors, or for a scalar input function composed of the scalar output function, to put it briefly. So we'll have v of x of t dotted with x prime of t. Let's clean this up a little bit. So this is going to be 1/2 m. Actually, that 1/2 is going to go away because I see that this is pretty much 2 times x prime times x double prime. So that's going to cancel out the 1/2. So we're going to be left with m times x prime of t dotted with x double prime of t. And let's do one other thing. I know that the gradient of v is negative f. So I can rewrite this as minus f of x of t dotted with x prime of t. And now here's where Newton's second law of motion is going to come in, because I know that f of x of t is equal to m times x double prime of t. So I can rewrite this as mx prime of t dot x double prime of t minus m x double prime of t. Oh, but I wrote an m. Interesting. X double prime of t dot x prime of t. And lo and behold, I just wrote the same thing twice, just with some rearranged terms. That's all 0. So we indeed showed that the derivative of this function was 0, which means thus 1/2 m x prime of t, the norm of that squared, plus v x of t. And again, that is the sum of the kinetic energy and the potential energy. That is constant. And we're done. So we showed that is true using Newton's second law of motion and the definition of a potential function.